Did some.
If I change also false. Sorry? So,
Am I on? Good morning. We'll start the session now. Uh, Today we'll be talking on the world of galaxies, and I'm N Hasan from Mano. So some of you probably are familiar with. क्या है प्रिया? We are looking at the world of galaxies, and some of you probably are familiar with it, but for completion and it's required that we cover this up. We'll be having more sessions on this next week, and then in November again. Next week, Professor Ajit Kimbhavi, who was the director of IUCA Pune, would be continuing. But today we'll have a very broad general overlook of the what galaxies are and in Milky Way in particular, and how our perspective has changed over these years. So, yeah, so galaxies are large collections of stars, gas, and dust. And when we say large collections, we mean billions or 100 billion stars, right? Collections of thousands or millions are not taken as galaxies. They should be running into billions or a few orders of 100 billion stars. Typical masses range from 10 to the power of 9 to 10 to the power of 12 solar masses. And mass of the sun, as you know, is 2 into 10 to the power of 30 kilograms. Typical sizes of galaxies are 100,000 light years. In kiloparsecs, it amounts to 30 kiloparsec. You are familiar with what light years are and what parsecs and what kiloparsecs are, so I shall not repeat here. And to remind you, billion is one followed by 9 zeros. So the first, so if you are lucky to be in a place where the skies are dark, clear, with no pollution, you will see what we see here on the left-hand side, a man looking at this beautiful sky of the Milky Way. This was something possible from Hyderabad to just 30 years from now when I was a student, but now it's impossible to see from any city. And the first maps of the Milky Way, the first map was given by Herschel, which we see right in the center. This is Herschel's galactic model given in 1784. And as you see on the right hand picture, what Herschel did was just a very small portion of the Milky Way as we understand it today. So the green dashed line is the extent of our Milky Way as we understand today, of the visible Milky Way. And Herschel could see only a small part of it. He assumed two things. He assumed that all stars had the same brightness, that was believed at that time. And he thought that if a star looked fainter, it was because of its distance, it was further off, and stars which were closer looked brighter. So he attributed the absolute apparent magnitude to the distance from the observer. And at that time, they had no understanding of interstellar medium, so obviously he didn't consider interstellar extinction. And it's understandable that he thought that sun was the center of uh, the, the galaxy. And because of technology, you could only to see to certain limits, approximately similar distances on either side from where we are observing. That's why he kind of assumed that the sun was in the middle. But interesting thing is, he did realize that it was some kind of a flat structure. Okay. Uh, this slide gives you a brief history of how our understanding of our universe has changed and of galaxies has changed. And there's a reason why I'm putting it up. In 1610, Galileo, he looked at the Milky Way through his telescope, and he saw that it comprised of many stars. People thought there was some fluid or gas there. It was called the Milky Way. But when he turned his telescopes to the skies, he realized that there were many, many stars, and that fuzzy, fluidy look was because of this innumerable stars, and the light was getting all uh, mixed up. 1755, Immanuel Kant theorized that the galaxy has a planar structure, and some nebulae might actually be entire galaxies by themselves. He gave the island universe concept. He said that there are many galaxies separated by large distances, and they do not have anything to do with each other. They are island universes. But this was not on any scientific grounds, it was only on a philosophical ground, right? So this was not an evidence for us to accept that at that time we realized there were more galaxies. 1774 to 1781, Messier, who was a comet hunter, he catalogued all nebulous objects. These objects disturbed him, so he made a list of objects which were fuzzy, nebulous, but which were not comets. And this catalog, interestingly, is very important for us now. And many of these nebulae are galaxies. Some are star forming regions, some are clusters, globular clusters, but many of these are galaxies. And this included the Andromeda galaxy, M31. 1781, 1802, William and Caroline Herschel, brother sister pair, conducted their first all sky survey and catalogued about 5,000 nebulae and resolving stars in some of these nebulae. Shapley in 1918 showed that the sun is not at the center of Milky Way. He looked at globular clusters, and these globular clusters were arranged in a spherical distribution, and the center of this spherical distribution was not where the sun was, but somewhere else. And he hence realized and said that the sun is not at the center of our Milky Way. Though he got his size of our Milky Way wrong, he estimated it to be much larger. 1920s, there was this Shapley-Curtis debate. Shapley believed that Milky Way was the only galaxy. The whole universe was just one galaxy, which was our Milky Way. But Curtis believed that there are many more galaxies other than the Milky Way. And this was settled by Hubble and Emerson's observations, and the debate was resolved and settled in favor of Curtis. They looked at some Cepheid variables and in Andromeda galaxy and found that Andromeda nebula was much further than the believed extent of our Milky Way, and they could resolve individual stars too in the Andromeda galaxy, establishing that Milky Way is not the only galaxy. There are many more. And their works following that uh, showed that yes, we live in a universe which has many, many galaxies. So why I want to bring to your notice is till 1920s, just 100 years from now, we had a very poor understanding of the universe and galaxies as such. We didn't know that there was one galaxy or more, and only 100 years back we got to know. So the history of research in galaxies is much younger, much shorter, and there's so much more to do. And astronomy is uh, driven by technology. We have better telescopes, better back-end instruments, better cameras, space-bound telescopes, so we are getting a better view of these same objects. We are observing them in different wavelengths, seeing different processes going on, and understanding the whole universe better, and galaxies in particular. So this is what our understanding of our Milky Way is today. We feel that it's a barred spiral galaxy, and the diameter of the disk is about 100,000 to 180,000 light years. The thickness of the disk is 2,000 light years. It is not uniformly thick, right? Uh, but it's about 2,000 light years. Our sun is not at the center of the galaxy. It is some two-third distance away, 28,000 light years away from the center. And the number of stars in our Milky Way are from about 100 to 400 billion stars. Mass of our Milky Way is about zero point 0.8 to 1.5 into 10 to the power of 12 solar masses. And the morphology over the years has been, uh, we understand, getting a better and better understanding of it. First, we thought it was a spiral galaxy, then we realized it was SB galaxy, then it was realized it was a barred spiral. So today it is a, we realize it's a barred spiral galaxy. So you would call it SBC. Yeah, so it's SB, SBC, or S capital B. And the RS indicate, these are refinements into the Hubble's sequence, which we'll be seeing soon. So it's a barred spiral galaxy, and it's a very difficult task. You would all realize that we are within the galaxy, and to understand its structure from within is very difficult. So this is done by looking at light coming from different directions, by more studying the dynamics, the motion of stars, and so on. And basically, from dynamical studies and others, you try to construct the shape of the galaxy and get an idea of the size of the galaxy. So here is a zoo of galaxies. Galaxies come in all kinds of shapes, sizes, and colors. Everything has a meaning to us. Color indicates the temperature of stars. Blue indicates hot young stars. Reddish indicate uh, cooler stars comparatively, or reddened by interstellar extinction. They come as ellipticals. They come as these cigar-shaped ones. They come as these beautiful spiral galaxies, or spiral with a bar in it, circular galaxies, and so on. Right? We are seeing these galaxies at random orientations. We are fixed in space, and these galaxies are scattered all around at different orientations. And sometimes we see them face on, sometimes we see them edge on. So sometimes we see them as an ellipse, sometimes as a circle, sometimes we can see the spiral features in it perfectly, and so on. So once people realized, when Hubble's observation showed that we live in a world of many galaxies, various classification schemes came up. That's basic nature of human beings. You classify leaves, you classify uh, roots, everything. And when you have a variety of shape of galaxies, you try to classify them. So the galaxies are classified in terms of their morphology or the chemical composition in it, whether they are basically have stars which are only having hydrogen being converted to helium, or they are richer in uh, elements, whether they have evolved, right? So DDO system, and there are various classification schemes. The simplest one is the Hubble's galaxy classification scheme. So Hubble distributed the galaxies basically in three groups. He said there were elliptical galaxies, spiral galaxies, and lenticulars. Ellipticals, he arranged them as E0, E1, E2, E7, depending on whether E0 were circular looking galaxies, E1 were slightly elliptical, and with the ratio of major axis to minor axis becoming larger and larger, the difference becoming larger, the ellipticity became larger. He went from E0 to E7. Spirals he distributed into two uh, sections: normal spirals and spirals with bars. So they were SA, SB, SC. SA are those spiral galaxies where central nucleus is big and prominent and spiral arms are closely bound. SB, the nucleus central bulge becomes smaller and the spiral arms slightly open out. And SC, the spiral arms are much widely open and the central bulge or the central nucleus becomes still smaller. S capital B, A, S capital B, B, and C again are similar but with a bar in it, where S, B, A are the bar with closely bound spiral arms, S capital B, B with arms slightly open, SBC with arms even opened out. And lenticulars, which he took, were sitting somewhere in between. They look like ellipticals. They had a large bulge and a disc-like feature, but the disc was featureless. And he arranged them in this the diagram which is given in the slides right below. Yeah, this was given sometime in 1930s, 1936, which is called the Hubble tuning fork diagram. And he noticed that there were some irregular galaxies which could not be put into any of these three bins, and he put them, brushed them under the carpet. He said there were these irregular galaxies and not many of them, and he said probably these galaxies would not, there was not sufficient matter in it to completely form into a galaxy, and it didn't fall in his morphology, so he preferred to ignore them. He took them as aberrations. But that was the time when there were other people like Zwicky and all who were very much interested in these irregulars. And even today, as we study galaxies, we realize these irregulars are the most interesting objects because these galaxies are evolving and they are interacting, and there are various reasons why they are irregular and so on. Right? So we'll be coming to these as we proceed. So though this scheme was just a morphological scheme, but people started believing that this is how galaxies are formed. They are formed as spherical mass flows in, gas accumulates due to some gravitational potential, star formation takes place, and you form spherical galaxies. And as it compresses and if there's a rotation, then it starts bulging on the equatorial plane and it becomes an elliptical galaxy. If the rotation is higher, then it becomes more and more flatter, so it goes from E0, E1 to E7, and then the disk appears, which makes it a lenticular, and then due to perturbations and other things, which at that time people didn't quite understand how it can happen. They thought these spiral arms appear and you get the spiral galaxies, right? So it was believed that from left to right, from ellipticals evolved to become spiral galaxies. But this is not true. Today we realize that the reverse can also happen. Spirals can also merge to form ellipticals and so on. And there's no one straightforward recipe for a galaxy to form and evolve into a specific shape and size. And today we realize that these galaxies are dynamical systems. They are constantly evolving in time, though we see them uh, uh, as as stagnant objects, as unevolving objects. It's because we are just our lifetimes are just moments in the lifetimes of these galaxies. So these galaxies change their shape over millions and billions of years. So a few things which we have realized in these years of research is that there is a very strong correlation between the black hole, which sits at the center of the galaxy, and the bulge, right? So most major galaxies have massive black holes sitting in the center, and our Milky Way too has uh, this massive black hole, and there is a direct correlation between the bulge and the black hole mass. So what we can understand from this is if you have a larger black hole at the center, then the bulge is larger and the disk probably is sitting inside, right? Secondly, uh, the disk is where the gas is, and gas is the raw material which creates stars. So uh, in the disk, you have star formation taking place, you have massive stars, you have bright objects, and if it's an active, it has a lot of gas-rich galaxy, and gases settle in the disk, then we often see it as a spiral galaxy, right? So depending on what kind of a bulge it is, which depends on the mass of the black hole, we could not see the disk in it, or it may not have sufficient gas to have ongoing star formation at that moment as we are observing. Okay, so bulges also come in a variety of types. We have classical bulges. Classical bulges, rule of the thumb, are formed from mergers, and the pseudo bulges, these are uh, they come from evolution, right? So these are classical bulges, these are spheroidals, which are very hard to see at low inclinations. They are often featureless. You don't see any spiral arms, bars, or rings in it, and contain mostly old stars, and it doesn't have much of dust or star forming regions. And they are kinematically hot, right? The motion of stars is very high. They are dynamically supported with velocity dispersion of the stars. Pseudo bulges, they are disc-like bulges. They are flat or almost as flat as discs. They may contain substructures, nuclear bars, spiral arms or rings. They usually show signs of dust obscuration, younger stellar populations, and ongoing star formation. And the stars, they are kinematically cold, and they're dynamically supported by the uh, rotational velocities of those stars. Then there are bulges uh, of which are boxy or peanut-shaped ones, where the central bulge looks like a box, or it may look like a peanut, right? So they show a boxy or a peanut-like morphology. They are usually featureless and show no signs of dust obscurations. young stellar populations or star forming regions. They are also kinetically hot, cold, and usually referred as pseudobulges. Right? So we will come to these morphologies of galaxies again later, where I'll be discussing Galfet and how we can, yeah, we'll do a little bit of uh, contour fitting to it and see whether we can understand the structure of the galaxy of this. Yeah, we can use IRAF does it very well, so we can do using that. Then when we uh, do Galfet, essentially what we do is we make mathematical models of galaxies, and if you have an image from an observation, the galaxy probably looks like, say, an elliptical galaxy, and you fit a model galaxy to that with the parameters of the minor axis and major axis, and the light decreasing by, there are various mathematical models, and then you subtract the image. From the image, we subtract the model, and if the model is good, then the residue you get is empty, you get a clean residue. But very often you get features. You see features which are hidden in it, which you normally to naked eye you would not see them, right? So Galfit, then you can have multiple component fitting and do this, and we can get the finer features in it. We can see whether the galaxies are remnants of mergers or not, and so on and so forth. So here we have uh, something like our Hubble's Turing fork diagram, but it has been refined by Cormandi and Bender. So this is a parallel sequence of galaxy classifications, which includes spheroidals, SPH, yeah, spheroidals, galaxies as bulgeless, exogalaxies, and we juxtapose them with irregular and irregular galaxies, right? So you have boxy, you have these ellipticals, and you have exogalaxies. These are the lenticulars which are here, and we have the spiral galaxies arranged below, right? So we have boxy, disky, and SO zeros, and then as the central bulge becomes smaller and the disk becomes more and more prominent, they, in the same way as Hubble did, SOA, SOP, SOC, and you get the spheroidals, and right. So somehow this arrangement kind of explains how the galaxies evolve in time, and they're categorized in terms of their uh, histories of formation and what are the initial conditions which can lead one or the other. So bulge formations of massive elliptical galaxies is often from early disruption followed by mergers, mostly minor mergers. Classical bulges could also from mergers, but the difference in the morphologies of classical bulges and ellipticals indicate that the different merger histories are needed to form classical bulges as compared to the ellipticals. These differences could be in the ratio of major to minor mergers, the ratio of gas poor to gas rich mergers, the total number of mergers, and the merger orbital parameters. Right. So these can also be done and tested with n-body simulations, and they are highly sophisticated tools which are made available for people to use, alter them, and run very meaningful simulations. So Gadget is one such, which is an extremely powerful one, which you could uh, install on your laptops and run them. And for when you have to run for millions of billions of particles, then probably you'll require a cluster or so somewhere, but the initial insight, the physics of how things work can be done on a simple machine too. So we'll be touching upon that too sometime in November. Uh, so what we realize today is our Milky Way belongs to a group of galaxies, and this is called the local group. There are about 54 companion galaxies to Milky Way. Most of them are dwarf galaxies. The other major galaxy is the Andromeda galaxy. In fact, Andromeda is about 2 times more larger than the Milky Way. And this gives you a schematic diagram of some of these galaxies which are around. And these dwarf galaxies have been have interacted, merged, or ripped off by our Milky Way, or are in the process of doing so, or would do so in future. So the whole system is a dynamical one, which constantly changes in time. And as these galaxies come close to each other, they deform each other and their morphologies change, their star formation rates change, and so on and so forth. These local groups, smaller groups of galaxies huddle together to form larger clusters of galaxies. And for example, we have Coma cluster. It has over 1,000 identified galaxies, mostly ellipticals and lenticular galaxies. It has a few spirals of younger ages, and many of them are popular near the outskirts of the cluster, right? And on the right hand side, we have the image of a portion of the Virgo cluster, comprising of 1,300, probably up to 2,000 galaxies. And it's a fairly heterogeneous mixture of spirals and ellipticals. It is very interesting to study uh, the morphology density relationship. If we can find out the numbers of spiral galaxies to ellipticals, and in different regions where they're crowded regions, uh, or they're separated from each other. This is something very interesting, and that would give a greater insight into why galaxies uh, have different shapes, and what goes into making of large elliptical galaxies and so on. And in many of these galaxy clusters, you see a massive CD galaxy, a massive elliptical galaxy sitting right at the center, and probably a monster which has gobbled up many other galaxies. So there are various environmental processes which uh, change, which change the galaxies and their shapes and so on. You have this ram pressure stripping. So interactions can lead to quenching of star forming. So I have an animation below which will imitate what you see on top. Probably you can notice the galaxy moving in the Coma cluster as this galaxy is plunging through the cluster, Abel cluster, sorry. There are these outflows, right, which is driving away cold gas from from the galaxy, right? So in the clusters of galaxy, the intercluster medium is very hot. It emits, shows up in X-rays, showing temperatures of millions of degrees. And as these galaxies fall through these clusters, then the uh, cold gas is stripped off, and it could lead to uh, uh, quenching of star formation, which is also called, starvation, right? So all kinds of weird names are being used in galaxy interaction. Galaxy harassment, galaxy strangulation, or cannibalism. And here we have all these images of various galaxies. ESO 137001, which is a spiral galaxy which is falling through a crammed galaxy cluster, and gas is being driven out from the disk. Of yeah, good examples of ram pressure stripping, right? So these are all these NGC 4254, right? All these outflows, and then the other one is when two galaxies come close to each other, uh, go past each other, or they collide with each other, which disturbs both the galaxies get uh, disturbed, or this dynamical harassment which results from these high-speed encounters of galaxies in clusters and with overall, right? So you see on the right side of a ring galaxy being formed. So what you see is probably it was a disk galaxy, and a compact one is coming and ramming slightly off center, and and you can see that there's there are a lot of blue stars here. So as the gas and dust gets pushed, it gets compressed, and there's a burst of star formation which takes place. So it promotes gas flows towards the galactic center, right? So when two galaxies come close to each other, it can compress gas and funnel it towards the center, leading to star formation. It could lead to heating up of the disk. Heating up the disk means the right. So this compression, a lot of gravitational energy is released, uh, and it strips off the outer. It can strip off the outer parts of the galaxies and so on. And the environmental processes three, there's this starvation of late growth by cold gas inflows and various things, right? So you have galaxy harassment, galaxy starvation, and galaxy cannibalism. So what we shall see here is NGC 4676 and its companion 4677. These are two galaxies which are also called the mice. They look like two mice, a mouse with a tail. Uh, it looks like there are two mice which are uh, hitting each other. And for a long time, it could not be understood till we had refined observations and better. So what we essentially see are two spiral galaxies, which are which are uh, colliding. Oh God. These are two spiral galaxies which are in the process of merging, and they would merge to form one big uh, elliptical galaxy, right? So here they are, we are seeing it at this stage, and they would finally merge to become one big elliptical galaxy. So in 1970s, Toomre and Toomre did their first refined simulations of galaxies. The history of galaxy interactions and simulations goes back to Homburg, where he used light valves to study galaxy interaction, because light also falls by 1 by r square law as gravity falls. But these simulations have improved over time, and when Toomre and Toomre with simplistic models showed how tidal forces create these tidal features, where you have a galaxy with a ring of stars around it and another one going past and pulling out tidal tails and showing how features are formed, how and as it continues to rotate, they become spiral arms. And when they showed that spiral galaxies can merge to form elliptical galaxies, people could not believe this, because this was something opposite to what people thought it was so. They had thought it was ellipticals which evolved to become spirals. But here the simulation showed that the spirals can come and form ellipticals. There were many things which people don't like because people had thought that astronomers thought that elliptical galaxies there was no gas in it, there was no star formation in it, and while spiral galaxy has a disk where you have gas in it, star formation going on, and the velocities of stars in elliptical galaxies were all kinds of tumbling orbits, while spiral galaxies, the stars in the disk had a uniform circular or elliptical motion about its center, and some of the galact stars in the halo had all kinds of these tumbling orbits. But right, so what they didn't realize is when these spiral galaxies which are spinning, they come and fall into each other, they churn up the whole thing. The whole thing gets flowed up, shuffled up, and it assumes a elliptical distribution, and it looks like an elliptical galaxy. And the gas is all, it's no more in the disk, it all gets diffused. So depending on how these galaxies collide, how they hit, it could either lead to star formation, excess of star formation, and many things which were not understood. That why did galaxies have different shapes? Why were some galaxies more active in star formation? Why were some galaxies deprived of star formation? And why were the AGNs active galactic nuclei in some and not in the others? All these got uh, convincingly answered with simulations, and as simulations have become more and more refined, where you don't consider only particle mechanics, but you also take into the account fluid dynamics and fluid mechanics of the whole thing, and you can do very meaningful simulations where you can induce star formations and the new stars interacting with the others and evolving as a whole together. So here it is, and here is an image of shells of stars observed around some elliptical galaxies. And if you had noticed that simulation, you will see that even in that simulation, we had these kind of shells which were there. Yeah, so these simulations can imitate uh, what you see out there in a very accurate and beautiful way. Right, but interesting, important thing is that's not only one set of initial conditions which can lead to a certain final structure. There can be many different initial conditions, right? So the initial conditions are not unique. There may be different sets of parameters which can use to get the same output finally. So when we are imitating and trying to create the mice or so, you have to do simulations many times with different angles with which these spiral galaxies approach each other, with different velocities they come, with different mass ratios, and with different uh, dark matter halos to surround them to keep these galaxies stable. Otherwise, a disk, if you just create a disk galaxy, the disk uh, gravitationally breaks up. So to stabilize it, you have to put a halo around it. So n-body simulations, it's an art by itself, and there are techniques with which you can improve the efficiency of your simulations, reduce the time, and so on and so forth. Yeah, so again, a picture of a giant elliptical galaxy where you can see at the core of the galaxy. This is a multi-waveband picture, and it shows at the center multiple cores, which is a sure sign of a merger remnant. Very often you see galaxies with multiple cores and they are counter rotating also. which very clearly indicates that these are merger imminent. So this is an example of cannibalized, a cannibal sitting in the space which has consumed a lot of small galaxies. So our local group is also not free of cannibalism. Like mentioned, there are about 54 galaxies, and this number over time would change because as our observations are becoming better, uh, we are able to distinguish one thing, is identify, observe more structures within a local neighborhood which could not be seen, very diffused uh, irregular galaxies which we could not observe earlier because of the limitations of observational of technology basically. And many objects which were thought to be globulars are turning out to be uh, dwarf galaxies. And right, so we are realizing that the dark matter content is much larger. uh, it should be better classified as dwarf to this, right? So exactly as our definitions over time are changing about planets and Pluto ceases to be a planet, similarly our definitions of a dwarf galaxy uh, clusters are getting more and more rigid and the demarcations are becoming more pronounced. So we have these 54 galaxies, the largest being the Andromeda galaxy, the second largest Milky Way, and both have spiral structures and both have a lot of small uh, galaxies around them. Our two close companions are the large Magellanic Cloud and the small Magellanic Cloud. So if you have the privilege of going or living in the southern hemisphere, we can see them on a dark night as patches. And Milky Way has about 15 satellite galaxies, and probably it has undergone many mergers. And I will show some evidence of it, which we are getting from the Gaia data that Milky Way has a disturbed disk. Uh, and right, and Sagittarius dwarf galaxy and Milky Way. So in the past, it has undergone a interaction with SMC and LMC about 10 to the power of 9 years back, and it is going to collide with Andromeda galaxy in future. So you have a cartoon of our um, Milky Way with the large and the small Magellanic Cloud and the Magellanic Stream. So these two had a close encounter with our Milky Way, with some material falling in and ripping off these two galaxies into these things. So many of you must have seen these simulations. There are many refined, good simulations of Milky Way and Andromeda colliding. They are about 2.2 million light years away, and the gap is closing at 500,000 kilometers an hour. And there's a likely collision after 3 billion years. And the whole process will go on for a billion years for them to merge to become one big elliptical galaxy. So we have a relook. Yeah, so till now what we have seen is our universe is not comprised of a single galaxy as it was thought up to 1920s, that the whole universe is not just our Milky Way galaxy. Our Milky Way galaxy is just one among trillions of galaxies uh, in space. You have many galaxies. Each galaxy has billion, 100 billion stars, and and these galaxies often clump together to form local groups. There are many field galaxies too. It's not necessary that all galaxies should belong to some cluster or some local group. There are many field galaxies, but there is a tendency that they are these small groups of galaxies, and they join together to form larger groups, and these superclusters, they form the whole universe. And the extent of our visible universe today is about 14 billion light years across. So we'll have a relook at our Milky Way. We started off with Herschel in 1700s, where he saw that our galaxy was a disk-like structure with sun at the center, uh, but he was seeing a very small portion of it. Then Shapley realized that uh, globular clusters are arranged in a spherical distribution which doesn't center where the sun is, and hence uh, inferred that sun was not at the center of the Milky Way. And the picture which we got was our galaxy was a spiral galaxy, which refined to show that it was a barred spiral. And the picture which we teach at master's level even today is we say our Milky Way has you have a disk, you have a bulge and a halo. The disk is rich in gas and the star formation is on, while the halo is devoid of gas. It has some globular clusters in it, which are old stars. There's no star formation going on. There are no uh, there's no gas in it, and 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 the motion of the stars in the halo are all these tumbling orbits, uh, and the disk, the stars go around the galactic center um, in circular or elliptical orbits. In fact, it also has a wavy motion. So there are times when the sun goes down the galactic disk, then goes up. So it's like a right. But these disks, the stars in the disk are going around the galactic center almost uniformly, while the stars in the halo are in all tumbling objects. So, what I want to show is what we understand galaxy as today, and like I said, we we see it as a barred spiral galaxy, SBC galaxy, uh, and uh, this RD gives the distance at which the light falls by uh, E. So it has an exponential disk where the light falls, it's brightest at the center and it exponentially falls. And the scale at which it falls by an amount E is given as 2.15. And the disk near our solar neighborhood is about 300 pc, and our sun is about 8.5 kiloparsecs from the center, and the whole galaxy is rotating. So our sun is located in the this, one of these arms, the Sagittarius arms, yeah, near the Orion spur, and 8.5 kiloparsecs from the center, while the whole extent is about 30 kiloparsecs of the visible. And this is sitting in a massive halo, and estimates of a halo is now running into hundreds of kiloparsecs, and and over that it's sitting into a dark matter halo. So what does a halo comprise of? It comprises of stars, and they are globular clusters, and these globular clusters were observed right all the way back in uh, by 1665 by Abraham, right, M80, and Messier in 1764, right? So they have all these globular clusters, and also it has dwarf galaxies. And Shapley, uh, 1938, is is one of the dwarf galaxies, right? So the and what else do we see here? We have stars, we have global clusters, we have dwarf galaxies, and we have stellar streams here, right? So the halo is not as devoid and boring as it was thought to be. You have hypervelocity stars there. They are stellar streams. They are star forming, new stars being formed of the disk at higher um, latitudes. People had thought that star formation takes place only in the disk, but you have some gas out there, and there are young stars being formed. And uh, this will be covered uh, later by Priya. So, how do we uh, get these extent of our halo? Uh, you have, like you know, in astronomy, you have standard handles and standard candles. If you know what is the standard size of an object, and if you know how, uh, yeah, if you know how big it should be, and how small it appears to us, we can estimate how far it is from us, right? So if you know that a certain object, a globular cluster should have a certain size, we can measure what it's appearing to us, and we can measure the distance to it. But more reliable estimates are from these standard candles. They are objects which have we have a very good understanding of their absolute magnitude, and if you know what its absolute magnitude is, and when from the observations we get the apparent magnitude, and from the distance modulus, uh, which we have discussed, m1 is m 2.5 log d, we can make estimates of the distance, right? So there are these standard candles. We have discussed that Cepheid variables have are good standard candles. So if we have a Cepheid variable which you, from their pulsation period, we can estimate their absolute magnitude, and from apparent we can find out this. Apart from, we have these RR Lyrae stars which fall on these um, horizontal branch, and you'll see that their absolute magnitude doesn't vary much. They are lying very closely bound into, right? So if you can identify these Lyrae stars in globular clusters, then from the apparent magnitudes, we can estimate uh, their distances, because their absolute magnitude is very tightly bound. Similarly, we have the old blue horizontal branch stars. These are also good standard candles. Then we have F-type stars. From the turn-off point, we can estimate their magnitude, yeah, from absolute magnitude, and hence estimate the distances. This method of estimating uh, uh, distances to globular clusters using RR Lyrae stars and using their velocities was discussed interestingly way back in 1951 by Perec, where he says in his paper, Motions of RR Lyrae Variables. RR Lyrae variable gives us systematic velocities with respect to the centroid of nearby stars of about 121 kilometers per second. Right? And 54 independently, there was another paper by Nancy and G. Roman, where again they looked at these RR Lyrae stars, and they write their galactic orbits are highly eccentric, and concentration of galactic plane is comparable to that of the globular clusters or the Lyrae stars. and said how we can use these Lyrae stars to make estimates to the distances, uh, yeah, um, uh, to the globular clusters using F-type stars and so on. So here's uh, the cartoon of our Milky Way galaxy and orbit of a star which is falling in from a high velocity, and we can do the back of an envelope kind of an estimate, very beautifully shown by Justin Reed in one of the Gaia schools. He says you can measure, you look at some high velocity stars, and you can very easily, I'll show the calculations which he makes, to make an estimate from what height it was falling. So if we assume that it is falling from a height from a certain location where its velocity, it's just barely hovering there, where the kinetic energy and the potential due to the galaxy just balances. And if it falls, what height should it fall from so that its velocity is what we measure here, right? So we look at the solar neighborhood, a small region in our around the sun, and of 50 parsecs around us, and look at the velocity of stars, and compared to the velocity of the other stars and these fast moving stars, we can get the velocity dispersions and get some estimates. So here's again a diagram from Perek's 1951's paper, where he looks at uh, stellar velocities. What you see on the y-axis are the velocities of stars and the number of stars which you have, right? So you see that most stars are falling in this region, right, which is about 140 kilometers per second. But some stars you see have 650 kilometers per second, right? So velocities are falling this way. Many of them are 80 kilometers, up to 80 kilometers per, yeah, 95, 80, and so on. But this is where we are getting most of the stars. Most of the stars are falling within this range. So velocity dispersion, roughly we can take it as this 140 and do our calculations. And then we'll use these 650, 625 kilometers per hour high velocity stars, right? So there are some stars which have tremendously high velocities, and with which we can estimate how far these stars will get chucked off and where will they end up, and give an estimate of how far our halo extends to, right? So these indicate that the halo must be huge, and it's like I said, yeah. So here's the velocity dispersion. Velocity dispersion is defined as the velocity root mean square velocity and the mean velocity square. You take the difference between them and take the root of it. And this is the famous virial equilibrium equation. When a dynamical system has dynamically evolved and settled, and that if right, so in other words, if you have a n-body system which is in dynamical equilibrium, it assumes this virial state where twice kinetic energy plus potential energy is zero. Is zero, right? And this is arrived very easily. You take moment of inertia uh, and you integrate it twice with respect to time, and you equate that the total energy should be less than zero for the system to be bound, and we get this expression. Important thing for us to know that a system which is virialized, if should obey this. Twice kinetic energy plus potential energy is zero, right? So these large uh, clusters of galaxies are are visualized systems, and this is a very interesting and important one. This also gives us estimates of our the dark matter in clusters and so on. Right. So kinetic energy is half m v square. I'm taking the dispersal square here, and potential is minus g m by r, where r is the size of the system, and which is we are taking as the radius where the uh, radius which contains half the stars of the system. So by using the virial equation half t, substituting here that half and 2 goes, and you get an estimate for the mass, and putting in the values of r as 8.5 and sigma square uh, as 140, we get a mass estimate of which is lying within a certain region of the sky, right? Which is 2.5 10 to the power of 11 solar masses, right? So this kind of indicates that there should be dark matter, otherwise these stars would escape from the system. The system will not be realized. Now again, when we look at this expression, we have kinetic energy half mv square and potential energy, which is this, and a star which is just bound, your kinetic and potential should both be equal. So you have half mv square minus gm should be 0, and m gives you v maximum square by r by this. And when we substitute the values of the high velocity stars b max as 650, we are getting mass estimate of a galaxy as again 10 to the power of 11 solar masses, right? So 2.5 or 4 for astronomers, it's fine because it's order of magnitude estimates, and it is giving you an estimates of how we can get mass of our galaxy. And doing this similar calculation here, reverting it around, and I'm substituting half mb square into 625, 650 you can put if you want, and gmm by 8.5, that's where the sun is. Apocenter, your velocity would become 0, and that will give you the maximum r. And so this expression should be equated to minus gmm by r max, and hence your r max is given by this minus gm by this thing. And if you do put in the masses of the galaxy and other things which we have computed, we get velocity R max as 112 kiloparsecs. So showing that the stellar halo extends up to hundreds of kiloparsecs, right? So they are very simple calculations which can give you very meaningful estimates of our Milky Way galaxy. So these are two scaling relations which are used to make estimates of mass of galaxies. We know that there is a mass luminosity relationship. A galaxy which is more luminous is more massive, and right. So we have this Faber-Jackson relationship, which gives the empirical power law for elliptical galaxies. So this is relation is between the luminosity and the velocity dispersion, and it follows somewhere like this. L is proportional to the velocity dispersion square. Yeah, velocity dispersion I have defined earlier. Root mean square velocity minus the average velocity difference of root of that. And we have the Tully-Fisher relationship, which is an empirical power law which is used for spiral galaxies, which gives a relation between luminosity and velocity, maximum velocity of the stars, right? So, uh, yeah, you can realize why we are using velocity dispersion in ellipticals and we are using max velocity uh, here. And again, it is L is proportional to V max to the power of lambda, where lambda has values between 3.5 to 4. In Faber-Jackson, we take velocity dispersion squared. Ellipticals have stars with all kinds of tumbling orbits. So the dispersion shows uh, how are these will give you an estimate of what is the mass of the system uh, which is holding such high dispersions. But here in a spiral galaxy, we take those stars which have maximum velocity, and yeah, there's not much of dispersion there because many of them which are moving in the disk, they have almost uniform motion, right? But interestingly, both are almost to the power of 4. In one, you have the velocity dispersion, we have other one, we have maximum velocities. Similarly, if you have dark matter content and so on, then those lambda values would change, which we shall not see now, but we'll discuss later. Uh, a few more slides to show what is new coming up with Gaia observations, with Gaia data. Priya will be covering Gaia data in detail. As you know, Gaia is on a great mission of observing billion stars with a very high accuracy of very good astrometry, getting their locations very precisely and their velocities very precisely. And with this data and the data releases which we have, if you plot the velocities, you see the scale here from 0 to 175 kilometers per second. There are different yellow, the color coded. The yellow indicates they are high velocity ones, and the red ones show uh, low velocity, and purple ones show less. So when we are looking at the disk of our galaxy, right near the galactic in the solar neighborhood, we are seeing different clumps. There are at least these 4 to 5 clumps where you see that they share a common velocity distribution types. So in a very small region, we see that there is a variation in their velocities. We have these Hercules clump, which are about 50 kilometers uh, per second, while you have these Hades and Pleiades and these which are showing very high velocities, right in the same neighborhood. So surely these are regions. So the disk is not as the stars in the disk do not move as uniformly as we thought they used to earlier. There is a big variety. And here we have, again from Gaia data, these velocities at different longitudes. This is at 0 longitude, this is at 45, 90, 135, 180, yeah, off the galactic center, towards the galactic center, and so on. And this shows that there is a lot of clumping, there's a lot of variation in their velocity distributions in this. So with the Gaia data, you could also see uh, the, the, the structure of our uh, disk of a galaxy. Yeah, just from the velocities which you see and so on. So with this, I come to the end of my presentation. Thank you. Yeah, so if there are any questions or so, then yeah. Okay, so now we will go into these questions. I hope you could hear me. The audio was fine. The slides could be seen. Um so we have, yeah, slightly. What causes the galaxies to increase their eccentricities so they become spherical to elliptical? Yeah, so uh, essentially, uh, like told me in my talk, initially people thought that ellipticals becomes you are sphericals, and because of rotation they start bulging. If it has a high rotation, right, then they would start bulging at the uh, equatorial plane, right? Precisely like most uh, planets are bulging. Like Earth's polar axis is shorter than the equatorial one because of the rotation. You have this matter, and if it's as it compresses, as it falls in, to conserve angular momentum, which is mr cross v, as your r is becoming smaller, your velocity starts becoming big, and the velocity on the equatorial plane is much larger than on higher latitudes. So it starts bulging at the equator. So from a spherical one to elliptical one, it could be the different rotational velocities of these objects which are forming galaxies, right? So in one, there is a, see, expecting that mass to fall in radially into something is absurd. It cannot. It can happen, but the probability should be extremely low that mass just is falling in radially from all around. There has to be some kind of an asymmetry always, and that asymmetry leads to that rotation of the cloud. So, and as it compresses, the rotation changes and then it starts bulging, right? So, when the right, so the understanding today is dark matter uh, halos were formed, which became the potentials for baryonic matter to accumulate, and these baryonic matter star formation started taking place, and they fell into each other to form bigger and bigger structure, and they formed galaxies. So, right, there were two scenarios. One, people thought that large structures were formed and then they fragmented, broke up to form smaller ones, from big to small. And the other one was smaller ones formed, which merged to form bigger one. And today, as science is progressing, evidence is increasing, the hierarchical formation from small to big is what is being accepted, right? And secondly, realize that if it is an ellipsoidal galaxy, when you are looking at it from a certain side, you can by chance see it as a circular galaxy, right? So circular galaxies could also be ellipsoidal, where uh, two of its axes have the same height, but one axis is long, right? So from one cross section, it will look like a circle, but from the other one, it will look like an ellipse. There are certain galaxies which are triaxial. You have a different galaxy, one each axis, x, y, and z, all axes are different in length, right? But because of this rotation, mostly they should be uh, two axes, right? They should be ellipsoidal. But triaxial can happen because of interaction, merging. So, okay, so, and then I've also shown that even spirals can merge to form ellipticals, and how they finally settle and from which angle do we see makes it look elliptical or spiral. What could Vandana ask? What could be a time frame of collision of two galaxies to form different shaped galaxies? Yeah, so these would run into billions of years. These time scales are very large, and interesting thing with galaxy interactions is if galaxies come and hit each other with very high relative velocity, then they would just comb through each other without any deformation and so on. So when these galaxies come close to each other, they may not even hit each other, they may go past. But if the relative velocity is less, then it takes a larger time for gravity to act, which can lead to uh, galaxies harassing, merging, ripping each other up. So when two galaxies come head on with a high velocity and hit, the chance of star to star collision is very low because they are more of empty spaces than there is matter, exactly like in an atom. If two atoms come and hit each other, the chance of nucleus hitting nucleus and an electron hitting another electron is very low. They are more of empty spaces than matter is. So when galaxies hit with very high velocities, they just comb through. But if the relative velocity is slow, then this happens. And most of those interactions which we would be interested in, which could lead to a change in morphology, as you have asked, they should be slow encounters, and the whole process takes billions of years. Billion. What would that? Abhishek asked why we end up with a flat galaxy. Are spherical galaxies uh, possible? Yes, we can end up with all kinds of galaxies. It See, even if you have a flat galaxy, like a spiral galaxy, it surely needs a halo for the disk to survive. Otherwise, just a disk on itself, matter cannot sit in a disk. If you, yeah, you imagine stars which are only separated in a disk, they would require very high velocities to keep them in that position, right? So they are sitting in these large dark matter halos. In fact, estimates show that these 90% of matter is dark matter, and what we are observing is only 10% of it. So, uh, yeah, and remember one thing: a galaxy which two spiral galaxies can merge to form an elliptical one, and after some time, the gas can settle down in the disk, the equatorial plane, and star formation begins there. And this same elliptical galaxy would start looking like a spiral galaxy, and and so on. So this process is on. The spiral galaxies can become ellipticals, can become spirals. Spirals merge to become ellipticals, and so on. So spirals with bars, the bars are also transient in time. They can break up to become normal spirals, and in normal spirals again they can become uh, these barred ones. So what we are seeing is only a snapshot uh, in the whole process of the life of a galaxy. So they are constantly changing the shape. And when we say a certain galaxy is spiral or elliptical, we are just talking about it as it appears to us as now. Oh, Vandana, some tragic news. So very sorry to hear. Hope all's fine. We wish her the best. Escar Rouse, how often can the mergers take place in a galaxy? So the whole process of galaxy interaction runs uh, into giga years. So a galaxy in its lifetime can undergo various mergers. And what is being observed that most of these are minor mergers. Many of these galaxies have smaller companions around it, and because of this galactic potential, they keep occurring, but it's very difficult to estimate how often, but it should run into uh, uh, billions of years, billions of years. It's not a very regular event, and it's a very slow event. Even when we are in a process of merging, say for example, at this moment, our Milky Way is in a process of merging with another one. Um, we would not see that cataclysmic event right away. The whole process is a slow one. I think that's a random process. Yeah, yeah. It's a random, and depending on where you are located in the cluster, whether your cluster center is very rich. Yeah, we have many galaxies around us, or there are few. That would define uh, the merger frequencies. During the merging process, will the gravitational waves produced at the center? Yeah, so when these black holes would start merging, yeah, when the galaxies come close and start merging, you would not expect gravitational waves being produced unless by chance some massive smaller black holes or neutron stars, they start coming and uh, merging themselves, but there will be minor events. But obviously, when the centers of the two galaxies start merging and the two black holes would start merging, they surely would produce gravitational waves. How are the ring galaxies gravitationally stable? Right. So ring galaxies, which we see, are in a certain state as of state, and they would not remain as a ring galaxy for a long enough time. It's a process where you probably have an object coming, a compact galaxy coming and hitting a disk-like object, a looser one, and creating a ripple in it, and and then after some time they would fall back. So I would expect that these ring galaxies, though they may live through our lifetimes, but at the scale of the life of galaxies, they would not remain so because they will not be stable. They would fall back, like the simulation which you must have observed when the spirals came. The spiral arms were created, matter was thrown off, and then they slowly fell back, and the whole thing settled to form one elliptical galaxy or so. So this would happen to these galaxies too. Do we see mergers at high redshift? Yes, there are observations of galaxies interacting with very high redshifts. Yes, there are observations. I can't give exact ones right now, but there are observations of uh, at very high redshifts where galaxies are in the process of merging and so on. And those stars, they are basically uh, metal poor stars, uh, right? Yeah. Yes. We do see. Yeah. So I think we can continue discussions with galaxies next weekend. We'll be having Professor Ajit Kimbhavi, and then I will be again continuing with galaxies later. Uh, so today we'll end today with no more questions, and we'll meet tomorrow with Tim Hamilton. He'll be discussing gravitational lensing and dark matter. Okay, thank you to all. Bye bye.